Welcome back to Neural Intel. Today, we're plunging into a really cutting-edge area of AI. It's all about how we're building models that don't just see and understand images, but can also, conjure up new ones from scratch.
Exactly. For a while now, we've had pretty separate AI for understanding images and, well, for generating them. The really exciting work now is happening in building unified models, ones that can do both inside the same framework.
Mm.
And the big question is, what's the smartest way to actually design and train these AI powerhouses?
And that's precisely what the paper we've been digging into is all about. It's called BLIP3-o, a family of fully open unified multimodal models, architecture, training, and dataset. So our mission today is to pull out the core technical ideas behind this BLIP3 family. These models are making waves in this unified space. We're going to look at how they've, cleverly combined different AI techniques to get some genuinely impressive results, both in understanding and creating visuals.
Yeah, the paper starts by pointing out this clear trend towards unification. It mentions models you might have heard of, like Janus, Show-O, Metamorph, and, of course, all the buzz around GPT-4o. The reasons for pushing towards a single model, they're pretty compelling, especially from a technical angle.
Okay, let's unpack why unification is such a hot topic then. What's the core advantage? Why have one model do both?
Well, think about it like this. If you have a single model, you can tap into the really sophisticated reasoning and instruction following skills that large language models already have, and you can apply those directly to image generation. So, for instance, a unified model can understand a prompt like an animal with a long nose and just visualize it. It doesn't need complex rephrasing or translation steps. The understanding is already baked in.
That's a great point. It's like leveraging the LLM's existing brain for visual tasks. What else? What's another key benefit?
Another really big one is enabling much smoother in-context learning. Imagine the model generates an image. Because it's the same model that also understands images, that output can directly feed into the next step, like editing that image or even having a visual chat about it. It makes the whole interaction much more coherent.
Right. So the AI can kind of remember and build on its own visual work. That sounds crucial for more complex stuff. And the paper suggests this is a step towards more general AI, AGR.
Exactly. The researchers definitely see this as moving towards that goal. Systems that can perceive, interpret, and generate diverse content in a much more integrated fashion. Now, looking at BLIP3-o specifically, how they tackle this, they use what they call a hybrid architecture.
Hybrid, meaning it borrows from different model types. The paper mentioned inspiration from GPT-4's rumored structure.
Precisely. They've combined the strengths of autoregressive models, the ones great in predicting sequences like text generation, with diffusion models. Diffusion models have just been incredible for generating really high-quality, detailed images. So their core research then really drills down into three key technical design choices within this hybrid setup.
All right, let's get into the nuts and bolts. What are these main areas they're experimenting with?
Okay, first up is image representations. Big question here. Do you use low-level pixel info, typically from VAE encoders, or do you go for high-level semantic features, the kind you get from CLIP image encoders? Second area, training objectives. They're looking at mean squared error MSE loss versus something called flow matching. How do these affect training speed and ultimately the quality of the generated images? And the third one is training strategies. Do you train understanding and generation together, like jointly, or do you do it sequentially, one after the other?
Okay, let's dig a bit deeper into that second point, the image generation choices. You mentioned VAEs and CLIP encoders. Can you give us a more intuitive technical feel for how they work here?
Absolutely. So both VAEs and CLIP encoders are basically ways to turn an image into a more compact, continuous format the model can work with, easier to handle than raw pixels. Variational autoencoders, VAEs, they act like really sophisticated compression tools for images. They learn to squeeze the image down into this structured, continuous latent space. Think of it like a digital blueprint. And crucially, they have a decoder that can reconstruct the image from that blueprint. Many powerful image generation models, the latent diffusion ones, actually operate in this compressed VAE space. It's way more efficient.
Okay, so VAEs give you a compressed reconstructible blueprint. How does CLIP compare them?
The CLIP encoder with a diffusion decoder takes a different angle. It's more focused on the meaning or the semantics of the image. CLIP itself is designed primarily to connect images and text descriptions. It understands what's in the image at a high level. To use it for generation, like in EMU2 or here in BLI3-o, they pair that CLIP encoder with a diffusion model. But this diffusion model is specifically fine-tuned to reconstruct images from those semantic CLIP features. A key thing about the CLIP encoder is that it compresses the image into a fixed number of continuous vectors. The paper says 64 vectors here, no matter the original image size. That's different for VAEs, right? Which might make longer blueprints for bigger images. Then the diffusion decoder takes these meaning-packed CLIP vectors and generates the detailed image.
So CLIP captures the essence, the meaning, and the diffusion decoder paints the picture.
Got it. Now, how do they actually train the model to generate these latent representations? You mentioned MSE loss and flow matching. Exactly. Once you've got these compressed representations, VAE or CLIP, the challenge is training an autoregressive model, one that predicts sequences, to actually generate them based on text. The paper explores two main ways to get this alignment right. First is MSE loss, means squared error. It's pretty direct. You take the model's predicted image features, compare them to the actual ground truth features, and calculate the average squared difference. It's common and relatively simple.
Simple, okay. But maybe not ideal for generation tasks.
Yeah, the paper points out that MSE loss tends to push the model towards more deterministic outputs. For the same text prompt, you might get very similar visual features every time. That can really limit the diversity, the richness of the images it generates. So the second approach they looked at is flow matching.
Flow matching. Sounds more sophisticated. What's the basic idea there?
It is more involved, yeah. Flow matching is a diffusion-based technique. It's designed to learn the underlying probability distribution of those continuous image representations. Instead of just predicting the target features directly, it learns to predict a velocity field. You can kind of think of it like guiding a flow, starting from random noise towards the actual distribution of real image features over time. And this allows for stochastic sampling. That means the model can generate different, but still plausible, image representations from the exact same text prompt, leads to more diverse, more realistic outputs. They use a diffusion transformer, a DIT, to actually predict these velocities.
Okay, so MSE is direct, but maybe less creative. Flow matching learns the whole style and variation, giving more diversity. Makes sense. The paper then looks at 3 specific combinations of these encoders and objectives, right? What were those?
Yeah, they tested 3 main pairings. First, CLIP plus MSE. Target is CLIP embeddings, trained with MSE loss. Then a diffusion decoder reconstructs the image from the predicted embeddings. Second, CLIP plus flow matching. Still targeting CLIP embeddings, but using flow matching to train the model to generate them. This actually involves 2 diffusion steps. One to get the CLIP embedding, another to decode that into pixels, better diversity. And third, VAE plus flow matching. Here, the target is the compressed VAE features, and flow matching is the objective. The autoregressive model predicts the VAE blueprint, and the VAE decoder generates the image. Interestingly, they didn't seem to explore VAE plus MSE in this particular framework.
Right, and what did the experiments show? Figure 4 in the paper laid out some results.
The results were pretty clear, actually. CLIP plus flow matching came out on top for prompt alignment, meaning the generated images really matched the text descriptions best. Now, VAE plus flow matching did score better on aesthetic quality, according to the FID metric.
But FID isn't always the whole story, is it?
Exactly. The paper rightly points out FID has limitations as the only measure of image quality. So, weighing everything, they concluded that CLIP plus flow matching was the most effective design overall for their unified model. It's like CLIP gives the strong conceptual grasp, and flow matching lets it paint multiple realistic versions of that concept, not just one predictable one.
That makes a lot of sense. You get the semantic grounding from CLIP and the generative diversity from flow matching. The paper highlighted 2 key findings from this analysis too, didn't it?
It did. First, autoregressive models seem to learn the semantic level features from CLIP more effectively than the lower level pixel features from VAEs, at least when you're integrating generation into a unified model like this. And second, using flow matching really does a better job capturing the complex distribution of real images. That leads directly to more sample diversity and generally better visual quality compared to just using MSE loss.
Okay, so CLIP plus flow matching seems to be the winner for the generation part. Now, how do you actually train a model that needs to do both understanding and generation? They looked at joint versus sequential training.
Yes, that's a fundamental choice. Joint training means you throw everything at the model at once, data for image understanding and data for image generation, all trained simultaneously. Models like Metamorph and Janus Pro took this route. The hope is maybe the model develops richer, shared internal knowledge that helps both tasks.
And the alternative, sequential, what does that look like?
Sequential training is a 2-stage process. First, you train the model only on image understanding tasks. get that really solid. Then in stage 2, you typically freeze the core language model part to part, the backbone, and only train the image generation module. LM Fusion and MetaQuery use this kind of strategy. Figure 5 in the paper shows this visually.
And why did the BLIP3-o team decide to go with sequential training?
They really emphasized its flexibility. By focusing first on mastering image understanding and locking that down, freezing it, they could guarantee it kept its strong comprehension abilities. Then, they could dedicate all the training firepower in the second phase just to optimizing generation without worrying about the two tasks sort of interfering with each other or needing to make trade-offs during training.
That seems practical. Build the foundation, then add the next layer, leveraging what you've already learned. So how did they actually put BLIP3-o together using this sequential approach and their CLIP plus flow matching preference?
Right, so BLIP3 comes in two sizes. There's an 8 billion parameter model trained on a mix of open source and proprietary data, and a smaller 4 billion parameter one trained only on open source data. And here's a really interesting pragmatic move.
Sure.
Because there are already excellent open source image understanding models out there, like Qwen 2.5 VL.
So they didn't need to reinvent the wheel.
Exactly. They actually skipped the initial image understanding training phase for BLIP3-o. They just built their generation module directly on top of the pre-existing Qwen 2.5 VL backbone. It's a powerful recipe, right? Leverage existing strength. Focus your innovation where it's needed most, in this case, generation.
Yeah, that is smart. Saves a lot of effort. So what are the specifics of the BLIP3-o architecture itself then?
Okay, for the big 8B model, they took the Qwen 2.5 VL7B instruct backbone, froze it, kept its weights fixed, and then trained the diffusion transformer, the DIT part, for image generation. That added about 1.4 billion trainable parameters specifically for generation. The smaller 4B model used the Qwen 2.5 VL3B instruct as its base. The DIT architecture itself is based on Lumina Next. That incorporates some recent improvements like NextAT, 3D rotary position embedding, sandwich normalization, RMS norm, and grouped query attention. These are all technical choices really aimed at making the generation efficient and high quality. Think of grouped query attention as a way for the model to efficiently look at different parts of the input at the same time.
Okay, sounds like they use some solid, up-to-date components. And the training process itself. 2 stages, you said?
Yes, 2 main phases, both focused purely on image generation since they started with the pre-trained Qwen. First was pre-training for image generation. The 8B model used a lot of data, around 55 million image caption pairs, a mix of public stuff like CC12M, SA1B, plus JourneyDB, and some proprietary data. And importantly, the captions were quite detailed. They actually used Qwen 2.5 VL7B instruct to generate them, averaging around 120 tokens each. They also mixed in about 10% shorter captions, like 20 tokens, just to make sure the model could handle different prompt lengths well. The 4B model used a similar approach, but with about 28 million public images. The basic prompt for this stage was simple. Please generate an image based on the following caption.
Right, so that first stage builds a broad capability. What about the second stage, the instruction tuning? Why was that needed?
Good question. The second stage was instruction tuning, specifically for image generation. After pre-training, they likely noticed areas where the model wasn't quite perfect. Things like generating complex human gestures accurately, getting common objects right, specific landmarks, or even rendering simple text within an image. These can be tricky. So, to fix these weak spots, they carefully curated a dataset of 60,000 high-quality prompt image pairs. They call it BLIP3-o 60K. And get this, they even use another advanced model, GPT-4o, to help generate examples targeting these specific problem areas.
Wow, using AI to train AI.
Exactly. They also pulled in prompts from JourneyDB and DLE3 to boost the overall visual appeal, the aesthetics. And this targeted tuning really paid off. It significantly improved how well the model followed complex instructions and the visual quality of the output. And they're releasing the 60K dataset, plus the pre-training data info, which is great for the research community. Creating 60K good examples, that must have been a huge effort, focusing on diversity and quality.
That's a major contribution itself. And the results, how did BLIP3-o stack up on the benchmarks? Tables 1 and 2 in the paper show this.
Yeah, the results are strong. Table 1 shows the AB model hitting state-of-the-art on most of the image understanding benchmarks they tested, inheriting that from Qwen. For image generation, Table 2 shows it gets really good scores on Genival and WISE, those measure prompt following and world knowledge. Its score on DPG bench was a bit lower compared to some others, though.
But wait, the paper mentioned a human evaluation because of that DPG bench score. What did the humans say?
Right, this was interesting. They did a head-to-head human study comparing BLIP3-o 8B with Janus Pro 7B using prompts from that same DPG bench. And even though Genus Pro had the higher automated DPG score, the human judges significantly preferred BLIP3O's images, both for visual quality and for how well they matched the prompts.
Huh. So the automated metric didn't capture human preference.
It seems like it. The paper suggests that BLIP3O, maybe because it was instruction tuned on that high-quality AI-generated data, learned to produce images that just resonated better with humans. Even if the specific metric didn't fully reflect that, it adapted really well to the style of that tuning data.
That's fascinating, the impact of AI-generated tuning data aligning better with human taste. Okay, lastly, what's next for BLIP3O? Future directions.
They're definitely not stopping here. They're actively working on extending BLI330 to do more things, like image editing, having multi-turn visual conversations, and doing interleave generation, mixing text and image generation in a dialogue. Their immediate next step seems to be focusing on image reconstruction.
Reconstruction.
Yeah, feeding an image into the understanding part and then having the generation part reconstruct that same image. It's about creating a really tight loop, a seamless bridge between seeing and creating.
Yeah.
And beyond that, they'll need to collect more specialized instruction tuning datasets to fine-tune the model for all these new downstream tasks.
Okay, so this deep dive really paints a picture of a very systematic, innovative approach to building these unified models. The key technical takeaways seem to be CLIP plus flow matching is a really effective combo for generation, balancing meaning and diversity, and sequential training, especially building on strong existing models, is a very practical path forward.
Precisely. BLIP3O is a significant advance. It achieves great results, and the fact that they're opening up the models and the data sets is a huge boost for the whole research community. It really pushes the field forward.
All right, let's try to crystallize what this means for you, our technically curious listener. BLIP3O really showcases this powerful trend in AI, the move towards single models that can fluidly, blend understanding and creation across different modes, like images and text. The technical work they did on image representations and training, especially using CLIP and flow matching, is leading to real leaps in the quality and the variety of AI-generated visuals.
Yeah, and what's really interesting is how effective their sequential training was, particularly building on Qwen 2.5 VL's existing understanding skills. It suggests maybe a more efficient path for building these super complex systems. Focus your innovation where it's most needed, like generation here, while smartly leveraging what already exists. And that whole instruction tuning part, using curated data, even getting help from another AI like GPT-4o, that points to this fascinating feedback loop developing in AI itself.
So thinking bigger picture, what does this point towards? Probably AI systems that can interact with the world much more holistically. They understand visual cues better, and they generate rich visual stuff with higher fidelity, sticking closer to instructions. Think about the impact on content creation, design, maybe even just how we interact with computers visually day to day.
Absolutely. And for your own exploration, if you want to dig deeper, definitely look into those core concepts. CLIP embeddings, diffusion models, especially flow matching, and the transformer architectures like DIT. The open source code and datasets for BLIP3O offer a fantastic chance for some real hands-on learning.
And maybe a final provocative thought to leave you with. The fact that a model learned so well from data generated by other AI systems, it raises some pretty fundamental questions about training data in the future, doesn't it? Will synthetic AI-generated data become the dominant force in shaping what these advanced AI systems can do? Something to mull over. Thanks for joining us for this deep dive on Neural Intel.